Okay, so this is number 3 from 5C. We have a car starting from rest at the top of a driveway that's sloped at an angle of 20 degrees with the horizontal. We know that on the car we're told that we have a frictional force, which is 4.0 times 10 to the third newtons. And at the bottom of the driveway, so the car does this, so VF here is equal, to 3.8 meters per second. We know that it started from rest, so VI equals 0. Well, what we want to know is the distance that it travels. So work equals the force. We'll put in that stupid cosine theta because we want to remember the following, that this is theta between the distance that it travels and the force doing the work on it. So the net force in this case. What other forces? So we know that the car is traveling down the driveway. What other forces do we have?
Gravity.
Gravity. So we have, that, which means, and I drew this not well to scale, it means that our F, oh boy, must be a good day.
For some people.
For some, yeah, not true. So remembering that we can transpose that F of gx up here, Fg would equal mass gravity, where F of gx would be sine theta mass gravity. So at this point, we know that because the net work that's done is, okay, so we've got net work is equal to force cosine theta times distance. And let me clean this up a little bit. This got untenably messy. We also know that the work is equal to the delta KE, right? So that would be the KE final minus the KE initial, which would be 1/2 mass final velocity squared minus 1/2 mass initial velocity squared. So what was the initial velocity? 0. So this is, work is equal to 1/2 mass times the final velocity squared. Well, work is also equal to this. So we can set those equal and we get this. Force times the cosine, and this would be the net force. Cosine of the angle between the net force and the motion times distance is equal to 1/2 the mass times the final velocity squared. We're solving, of course, for distance. So the distance is equal to what? Gesundheit. 1/2.
Squared over 2.
Yeah, O over F cosine theta, F net cosine theta. And yes, of course, you can do distance equals mvf squared over 2f times cosine, net force cosine theta. Okay, that sounds like a little bit more than I found a locker with interesting things in it. So your net force here, you have to look at sum of forces. Sorry to give you a flashback to chapter 4. Yeah, I know. If you look at the sum of forces, and assuming we've tilted the y-axis, what you have, of course, is the F of gx plus the frictional force. And, you know, basically they're in opposition, so one is going to be a negative, one's going to be a positive. You can do the Cartesian system and call the frictional force positive and the force of gravity on the x negative. You can flip those, whatever you care to do, but you're subtracting the frictional force from the force of gravity. We know it has to be less than the force of gravity on the x because we are told that the vehicle is rolling down that hill. So we know that the gravity is not enough to hold it back. So that's how you get, so we know then that, this piece is your net force. Now the good question is, what's the angle between the net force and the direction of travel? You tell me. Because that cosine theta is going to be the angle between the direction that the object is traveling, the distance, and the net force on it. So we know the net force is on the x-axis. We know good grief, net force is given by this. So the net force, which side's going to win? The net force is going to be this way. What's the angle between the net force and the direction of travel? 0. Yeah. So what's the cosine of 0? 1. So you're multiplying by 1. If they were in opposition, if the net force, and this happens when you're slowing something down, like due to friction, if the net force, this is sort of a general comment, if F net is this way, but the direction of travel is this way, then it's cosine of 180, which is negative 1. So, yeah. Okay, so does that get you, anybody who had a question on 3, does that get you what you need? Okay, let's go to number 4. All right, so number 4, we've got a bobsled being pushed. It doesn't say that it's a frictionless surface. It doesn't say how much force they're exerting. Oh, we're looking for net force on the bobsled. So what we know is that the work done is equal to the delta KE. So the work done is equal to final minus initial. And we'll just kind of shortcut that and say it's equal to, 1/2 mvf squared minus 1/2 mvi squared. And the work done is also equal to the net force cosine theta times the distance it's pushed. And we're given the mass of the bobsled, 75 kilograms. We're given the distance it's pushed, 4.5 meters. We're given VF of 6.0 meters per second, and VI was 0 because it was from rest. So we want the net force. We're looking for this. Oopsie. Okay, so we know that because initial velocity was 0, that goes away. We know that 1/2 mvf squared equals net force cosine theta d. And it appears, it's a terrible cosine theta, it appears here that the theta between the net force and the distance it's pushed would be 0 because we're told that they're pushing it and they get it going. We're not told, it shoves them backwards across the surface. So, and we are solving for this. So mvf squared over 2 cosine theta d. And remember that this is theta between F net and D, which in this case appears to be 0, would give us F net. Does that give you what you need? I'm not sure who had the question on this one. Okay, so we basically just take the two things work is equal to, set them equal, and solve. Let's go on to number 5. Number 5 is the classic. I will tell you that number 5 is the classic. It's such a classic that some version of this question always appears on the Chapter 5 test. That's not a hint, that's just a flat-out statement. It's pretty clear. Okay, so we have a 10 kilogram crate. It is being pulled up a rough incline. It has a VI of 1.5 meters per second. It moves up this incline. There is a pulling force, so force of the puller is 100 newtons. We have FG. Of course, we have FGY, FGX. I'm drawing this not to scale at all. We have FN, which I should have made a different color, but I didn't. Oops. The angle here is 15 degrees. We are given a coefficient of friction. We know that there is some frictional force. And it would be kinetic, of course. And the crate moves a distance of 7.5 meters. So, find the work done by Earth's gravity on the crate. This is great because this really gets to a very good illustration of how multiple things can be doing work on the same object. So we know that work done by gravity is equal to the force of gravity on the axis that forces act on the same axis as the motion. So in this case, it's force of gravity on the x, which is going to be Fg sine theta 1, we'll call it, this being theta 1, times the cosine of theta, where this is theta between f of gx and the distance. So what direction is f of gx working on this crate? Down the ramp. What direction is the crate moving on the ramp? Up the ramp. So what's the angle between those two? 180. So the work done by gravity is equal to, this would be what? Mass, gravity, sine of 15, and then times distance, times cosine of 180, times the distance that we move the crate. So the work done by gravity is going to be positive or negative?
Negative.
Negative. Gravity is working against you. Now the crate's still moving because there's more work being done on the crate by the puller than there is by gravity. So we've got that one. We're asked to find the work done by friction. So let's set this aside. Okay, so the work done by friction is equal to the force of friction times the cosine of theta, again, where theta is the angle between the force of friction and the distance, So work done by friction. Well, how do we find the force of friction? We'll have to sort of shrink this. We know that mu k equals fk Fn. Flashbacks to chapter 4, but it's not that bad. So we'll go ahead and start back up. So work of friction then would be force of friction. To get that, we're going to have to do what? Mu k Fn equals Fk. To get Fn, what do we have to do? Oh, sum of forces on the y. So sum of forces on the y would be Fn and f of gy. So you just have to look back to your picture. That means, of course, that Fn is the negative of f of gy. So negative of mass gravity cosine theta. So there are a lot of layers in this. So if we wanted to sort of nest all of that, we would have mass gravity cosine of 15. To get the cosine that's referenced in the work problem, we have to look back to the angle between the work that's being done by friction and the direction that the object is traveling. What's that angle?
If it's being,
It's being pulled up the ramp. Which direction is friction working?
negative.
Negative. So that would be cosine of 180 times the distance it's pulled. And like I said, I put a problem just like this on the Chapter 5 test every single year.
The 5-part,
Pardon?
the 5 parts of it?
Yep. Okay. Looking at C. The work done by the puller. So the work done by the puller would equal the force of the puller times cosine theta. Again, where theta is the angle between the force of the puller and the motion. What's the angle between the force of the puller and the motion? 0. Yeah, I can't do it with my stylus. Times the distance it's being pulled. That one's the most straightforward because it's just a given. Now, whoops, for D, there are multiple ways to approach this. Multiple ways to approach this. So, one way you could approach this, changing kinetic energy, would be the work equals delta KE. The net work is the change in kinetic energy. So really, what are we looking for when we look for the change in kinetic energy? We're looking for the net work done on the crate. How would you find that? Sum of forces. Because the net work is equal to the net force, again, cosine theta, times the distance. Now, what's theta between the net force and the direction it's moving? 0. Because if it, that's the direction it's accelerating, is up the ramp. Now, once you find this net work, can you find the final velocity of the crate? Sure. How do you do that? Well, because whatever value you get for this F net is equal to 1/2 mvf squared minus 1/2 mvi squared, and it's just a matter of solving for that. So at that point, it's just algebra. Questions, comments, concerns?
So for D, you'd have to find VF.
Yeah, for E, you have to find VF.
It says be able to solve for changing kinetic.
No, you do not have to find E to find D. This is D. This is the net work. Because that's equal to the delta KE. Here, let's back that up a second. Okay. Let me shrink this. Ooh, it's responding very slowly. I don't know why. Okay. So delta KE is equal to the net work, which is equal to the net force times cosine theta d. So if you're finding this value, you've just found your delta KE.
Oh,
Then once you have delta KE, that's equal to the 1/2 mvf squared minus 1/2 mvi squared. I should clarify that that's delta KE, not just KE. Okay, questions, comments, concerns? So, at this point, you have a little less than 30 minutes. I have a FIP quiz for you. It's got 2 questions. How about we go ahead and start it, because I don't want to totally blow the day. And if you're not finished, you can finish it as a take-home. I think many of you will finish it. I will not do bonuses for perfects that are finished as take-homes, But if you have a study hall next, you're welcome to sit here if you think you can nail the bonus. So